All right, so what do we have here? Here we have a table seen from above, and its radius is L, and the mass is sliding here on a ring that is placed a sort of wall. So it's sliding against that wall, which has a friction coefficient, μ. And the table itself is frictionless. So the friction force this mass will feel is against the ring, and when it's gliding, that force is in the opposite direction of the velocity. Here you see the initial velocity v₀, and here you see the friction force μ times n, and n is normally the pressure against the surface of the ring. That is usually in our problems in physics, mg. But in this case, it's not mg, because the force against the surface, the ring surface, is due to another force, which we call the centrifugal force. And it's mv² divided by the radius L. So this is the situation. So what we have, according to Newton's second law, we have F equal ma. Okay, and in this case, the only force acting on this mass here is the friction force. There is a gravitation force, but it doesn't matter because there is no friction against the table. So that force is μ n, and that force n is the force against the surface. In this case, the centrifugal force. So that is mv² over radius L. And this equal ma. And something we need to know about friction, it is if you have a velocity here, v₀, and we know that this mass here, after a while, will slow down. So that means that the acceleration must be negative. This is not what we see here, so sign is important. So I'm going to introduce here, let me see here. So the minus sign. There. Okay, so then we can write the acceleration. A equal, but by definition that is dv dt. And the mass cancel, so we have minus μ divided by L v². Yeah, that's it, right? And find the velocity of the block at a later time. That means find the velocity as a function of time. So we're going to solve a differential equation here. So we will multiply with dt here, dv dt dt equal minus m over L v square dt. And this thing here is just a differential dv. So dv, and let's that's equivalent to this. Move over this v squared to that left side. So we have this v squared dv equal minus L dt. And then we integrate both sides. So and this are constants, so we break it down immediately. And let's say the time from the start is 0, and at a later time t. And don't confuse that it is the same notation here. In physics we can cheat a little bit. And here, well, it was not the t, here it was dv, right? dv. And our exercise here is to find the primitive function of this. And it turns out to be minus v inverse like this. And here the limits are v0 to b. So v0 equal, and here t simply. And further, so what we have is this minus 1 over v plus 1 over v0 equal minus this. Okay. And which is equivalent to 1 over v equal 1 over v0 plus L t. And now we should make a common denominator. So like that. Now we can add them together. And then we can find that b equal what? It is this simply. And then we divide by L to make it a little bit simpler. And that is the velocity as a function of t. And if you put in t equals 0, that disappears and you get b0, as we already knew. So that part of the problem is solved. it is this one. So yeah, we did it. Great. And now we shall find the position of the block at a later time. Okay. And what we have done is v, that's actually dx dt. And x, in my case here, is the distance we are traveling here. So it's just the distance here along the circle. So dx dt equal v0 divided by 1 plus kt. So this is a constant here. Let's call that k. And again, multiply with dt. And then you have dx here. v0 1 plus kt dt. Then we integrate both sides. X, let's say that's 0 from the start, t equals 0, and x at a later time. And time is 0 at the beginning and t at the later. So here it is just x equal v0. And now you will have to find a primitive function of this. And that is 1 over k logarithm 1 plus kt. And let's just solve it. So this is x equal v0 over k ln 1 plus kt. And when you put in 0, you will get ln 1, but that is 0. So this is x as a function of t. And how could I know that this is the primitive function? It has to do with the following thing. If you take the derivative of the logarithm function, having a function fx, that is equal to 1 over fx and multiplied with the derivative. So the primitive function, when we take the derivative of this, you must get this function in the integral. So when we differentiate this one, you will get 1 over kt and then times k. Then that's why I had the 1 over k here. So it takes out. And then, so this is just absolutely fine, no problem whatsoever. So the thing is, we have now solved this problem too. So thank you very much for viewing this, and see you later.